Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study a result regarding polynomial rings, and the result is, I have written it as a theorem, a polynomial ring which we have denoted by f of x is a principal ideal ring. Now polynomial ring we have studied in our earlier lecture is a set of polynomials whose coefficients are elements of this field F. And this polynomial ring is a principal ideal ring. Now what is the principal ideal ring, that we shall revise first, and for that purpose we know already that is what is the meaning of ideal of a ring, and then what is meaning of principal ideal of ring. Principal ideal ring. Ideal is non-empty subset U of R, and if it satisfies two conditions. U is subgroup of R under addition, and second is for every U belongs to U, element in U, and R belongs to R, both the product UR and RU is in U. If these two conditions are satisfied by U, then U is ideal of ring R. And secondly, what is a principal ideal ring? It's an integral domain R, or it is also a principal ideal ring, or it is also known as principal ideal domain. And an integral domain R is a principal ideal ring if every ideal A in R is of the form A generated by an element A for some A belongs to R, and or this has the expression that A is generated by A, small a means every element of the ideal capital A is multiple of this small a. Then we can say that A is generated by, this ideal is generated by the element small a. So this is the meaning, and therefore in this theorem we have to prove that every ideal of this ring, polynomial ring, is a principal ideal, means generated by some element, and elements of polynomial ring are polynomial itself, and therefore if we consider an ideal U of a polynomial ring, then we have to show that that ideal is generated by some polynomial. That we shall prove in the proof of the theorem. So first we shall suppose U is ideal of this polynomial ring. Let U be any ideal. Every ideal must be of this form. So therefore we shall consider arbitrary ideal as U. U be any ideal of polynomial ring of a polynomial ring. F of x, where U is different from the 0 ideal. Ideal generated by 0, because there are two obvious or trivial ideals of a ring, 0 ideal and the ring itself. 0 ideal will contain only 0 elements. So therefore we shall consider proper ideal, and that is different from 0. Further, let L of x, elements of this U is subset of now f of x, means elements of U as well as the ring f of x are polynomials, and let L of x be the lowest degree polynomial. Polynomial in U. And we shall consider another polynomial h of x in arbitrary polynomial in U. Let h of x be any or arbitrary any polynomial in U. So two polynomials we have considered in U itself, what is the difference in this? L of x is the lowest degree polynomial and h of x is any polynomial in U. Now we shall apply the division algorithm in this polynomial ring. These are the polynomials in U, means these are polynomials in f of x, because U is subset of f of x. We assumed U is ideal of f of x, and therefore these are the polynomials in f of x by division algorithm in. There exist polynomials, and we shall denote the polynomials as in our division algorithm we have denoted qx and rx, q of x and r of x in f of x, such that the relation is such that this h of x is written as or expressed as q of x into L of x plus r of x, where r of x is either 0 or degree of r of x is less than degree of L of x. This is the division algorithm. You refer the earlier our lecture division algorithm in polynomial rings, where we have proved the division algorithm theorem. So for these two polynomials Lx and Hx, there exist another polynomials Qx, Rx, such that h of x is equal to q of x, L of x plus r of x, and condition for r of x is either 0 or degree of r of x is less than degree of L of x, and we may refer this together as statement 1. Now next we shall write from this the expression for r of x. So this gives therefore we have r of x is equal to h of x minus q of x into L of x. This expression we shall have. Now we may suppose this as second, and now we see the right side of it. U is ideal of f of x. U is an ideal of f of x, and we have q of x is in f of x. See, q and r in f of x, and what about L of x? L of x is in U. See, L of x is the lowest degree polynomial in U. L of x belongs to U, R of x belongs to f of x. U is an ideal of f of x, and L of x is in U, R of x is in f, and therefore by definition of ideal, second condition of ideal, their product must be again in U. Then Lx or Qx into see, we want here Q, not R. Q of x. Q of x is in f, and L of x is in U, Q of x is in f, and therefore its product Qx into Lx. This is definition of ideal. Qx into Lx belongs to U. Also, see, h of x is in U. H of x belongs to U, and U is subgroup. This is first condition of ideal, subgroup under addition. Subgroup of f of x under addition. And therefore, see the difference of these two, that is hx minus this, its additive inverse exists, and therefore the addition of this h of x and additive inverse of this means actually the subtraction. Therefore h of x minus q of x into L of x, this must be in U, because both these elements are in U, and therefore their addition as well as their difference must also be in U, because it is a subgroup. And but what is this? This is exactly R of x, that is R of x belongs to U. And R of x, already we have considered this the existence of this in f of x, and now we have shown that it is also in U. And therefore now there are two conditions for R of x, either it is 0 or degree of R of x is less than degree of L of x. Now which of them is possible? By assumption, L of x is the lowest degree polynomial in U, and therefore degree of R of x cannot be less than degree of L of x. By assumption, Lx is the lowest degree polynomial in U. Therefore degree of R of x cannot be less than degree of L of x, and thus we must have this possibility is discarded, is not possible, and therefore we must have Rx is equal to 0, and thus we have R of x is equal to 0, and we put this in 1. Here it is all the statement is together 1, and thus the expression for h of x becomes qx into Lx. Therefore from 1 h of x is equal to q of x into L of x. And what this shows, that hx is any arbitrary polynomial in U and it is multiple of L of x. So this shows that hx is multiple of L of x. H of x belongs to U is a multiple of L of x in U, and that means U is generated by L of x. U is generated by L of x, or every polynomial in U is a multiple of L of x, and this shows that U is principal ideal, and therefore the ring f of x becomes principal ideal ring. Thus every ideal in f of x is a principal ideal. Hence f of x is a principal ideal ring or principal ideal domain. This proves the theorem. So thus considering a polynomial ring and f of x and an ideal U in this polynomial ring, we have shown that U is generated by a polynomial L of x of lowest degree, and that means this is arbitrary, means every ideal in this polynomial ring is a principal ideal, and therefore the polynomial ring is principal ideal ring or principal ideal domain. So we have proved the theorem. I hope you can understand this theorem. Thank you for watching the lecture.